Well, it's great that I have the opportunity to introduce you. Naftali Tishby is going to talk today about the informational bottleneck as an informational lens. Go ahead, Tali.
All right, thank you. Do you hear me and see the slides?
Perfect, yes.
Yeah. So it's really a pleasure to be here. This pleasure and honor to talk to this audience. We all have to get used to this way of giving talks. I mean, it's first of all, I turned on the Microsoft PowerPoint speech recognition subtitles, which is actually I found it very useful on such talks, and it's actually a wonderful example of today's abilities in deep learning. 20 years ago, or even more than that, when I worked a little bit on speech recognition, I could only dream of anything that works so smoothly and nicely. Of course, there are mistakes, but considering the accent and the type of words we're using, this is quite incredible. So I hope you find it useful. So this talk is, to me, just like an invited talk to talk about a question I've been working on for many years, which is precisely, or at least one way to define it, as an information lens, in the very precise sense of it. And I'm going to focus essentially on, assuming that not everybody here know what the information bottleneck is, I want to introduce it in a somewhat a different way and actually relate it to some of the questions we already heard in these workshops. In particular, I want to relate to the question of how many bits are needed to predict the property of a pattern. I mean, this is really an extension of a very specific question we had yesterday from Mary about polynomials, and it turned out to be a very specific aspect of the questions, which we are trying to answer in a much more general and, of course, much more stochastic and less precise way than we could talk when we talk about polynomials, but it's essentially the same type of question. And once I pose this question, I'm going to show you how we answer it, and the way the answer turns out to be exceedingly simple. I mean, essentially very complex questions like, is this pattern, which can be a pixels of an image, is it me or not me, or is it a dog or a cat, or is this a collection or a huge collection of bits, can really give me 1 or 2 or 4 or 10 bits, which I need to, and how is this information encoded and distributed in the data? So this is a very complex question, actually very generic question, and I want to argue that this question comes again and again in many different fields. Has essentially, at least asymptotically in the size of the pattern, a very simple answer, which depends on only 2 quantities, 2 information theoretic quantities, which depends on essentially how you represent the pattern. So this is how it is related to representation learning, and essentially everything is focused on two entities. One is the encoder of the pattern, the map from the pattern to the representation, and the other one is the decoder. What is it that you're interested to extract out of this representation? And there may be many things that you want to extract out of the representation. There can be also different things. And these 2 quantities of mutual information, the mutual information of the encoder and the mutual information of the decoder, are going to run through the talk and the story I'm telling you today. And actually, I'm going to argue that even biology, at some sense, in some AI and biology actually are bound to the trade-off between the mutual information of the encoder of the decoder of the representation. And actually, this gives us this 2-dimensional representation is what we call the information plan representation. And this actually gives us, in many ways, all the hints about the structure of the problem itself and about the nature of the encoder, the decoder in general. And I'll show you a little bit just the taste or the flavor of the way we use this representation, this optimal representation, the one which actually optimizes the trade-off between the 2 things, to talk about typical learning in general and about some twist that this view makes of learning theory. And then I'm going to give you maybe the best application so far of this framework, which is deep learning itself. So you already heard how much deep learning change the world. And in some sense, this is one of the most interesting open questions we have in certainly machine learning, but maybe in many other fields. I mean, why and how this complicated machine works so well. And so I'm going to give you, to go through some of the main understanding we developed over the past few years of the connection between this information bottleneck lens, if you want, and what happens in the layers of the vanilla flavor feed-forward deep learning. But this is, I think, a very interesting story. Then I'm going to focus on something which is very much on my mind in the past few years, which is the connection between the geometry of or the topology, if you want, of the representations and this information bottleneck trade-off, and how essentially the critical points of this trade-off, which reminds or looks very similar to phase transitions in a thermodynamic system, how these topological transitions are related to the layers of deep learning and maybe other computational issues like the time it takes to converge to a good representation and so on, and why I believe that there is some connection between the critical points of the information bottleneck and the intermediate representations that emerge in the layers of deep neural networks. And this will probably get me to the end of my talk. So what is the information bottleneck? So this name and idea was introduced when I was actually at NEC with Bill Bialik and Fernando Pereira, who actually worked with me on language-related questions 10 years earlier when I was still at Bell Labs, out of which this concept and this abstraction emerged, which is essentially where is the relevant information in very complex data like speech or images or biology, DNA or spike in nerve cells, whatever you have in mind. And all of them have a similar essential questions. I mean, so again, quoting Mary Waters' wonderful talk yesterday about the information in polynomials. I mean, she asked this precise question: how many bits are needed to predict a point on a polynomial, and gave very elegant, somewhat surprising answer that if you are not asking about the number of points that you need on the polynomial, but rather bits, then you can actually save some bits, and maybe asymptotically even many bits, by looking at some sort of distributed representation. I mean, so it's not one point, you can collect some bits from many points and eventually make predictions about other points on this polynomial. So I hope that some of you remember this talk. It was really a very nice example of a very precise, simple looking question, which actually have a very deep answer. So in some sense, we are trying to ask a much more general question, and we've been trying to do it for a long time. So, which is essentially given a distribution of two variables, which X, which I think of a complex like pixels of an image or piece of speech or whatever it is that you have in mind, it should be large enough so that I can really treat it asymptotically in some sense and treat it, and then some property of the pattern, which may be, is it me in the picture or what is the translation of this sentence and so on. And this is what I call Y. So these two variables are in general related to each other. So essentially the question we're asking is how many bits are needed or I need to get from the pattern X, and you can actually think about it as binary yes/no questions on the pattern X, some sort of measurements on X, binary measurements on X, in order to predict that property I'm interested, which is Y. So even if I know this distribution, this is still a very interesting question, just as in the simple example of the polynomials. I mean, this is not obvious how many bits are needed. And it's very much not obvious that you can really answer this question in some general way. And indeed, the information theory, I claim, gives us precisely not only the way to answer it, but just using Shannon's concepts of code and of source coding and channel coding in some sense, both of them, actually noisy source coding, Rate-Distortion theory, and noisy channel coding, I mean, with some cost on the channel, both of them are combined somehow to answer this very different question. This is not a communication question, but exactly the same mechanism, the same type of proofs that Shannon used in his channel and in his coding theorems are needed and used here in order to answer this very general question. And of course, we can do it for, in some sense, using the machinery of information theory, which is also the machinery of statistical physics. We need large, and we talk about typical, not worst case, typical patterns. So of course, I'm not going to say too much about it. I'm saying a little bit, but when there is a large random variable, we know that there's some sort of, under some conditions, there's some sort of concentration theorems that tell us that most patterns are going to be typical in some sense. And this is precisely what I need here in order to prove things. And then what we are looking for is finding a compact representation, which I call X hat, which from which, so this is very different from the type of generalization bound that we had last night, like a conditional mutual information or things like this. I'm talking about a single pattern sampled from this random variable X, like a single image or a single piece of speech or whatever. And I'm talking about a map of this particular pattern to a representation, which I call X hat. But I want this representation to be efficient in the sense that I can make a prediction of this unknown entity property of the pattern, or known. I want to predict it, or I want to learn from labeled data how to predict it on unseen data. So this is really the fundamental question in machine learning. And it's also the fundamental question in many, many different fields, including biology, as I'm going to claim later on. And of course, in order to do this, I'm going to introduce, just in the spirit of information theory, I'm going to look for a stochastic map from the patterns to their representation. It's a single instance. I'm not mapping blocks here. I'm just thinking the pattern itself is large enough. And I hope you hear me, because I have some internet problems here. And of course, using a decoder, which is mapped from the representation to the label. So everything eventually focus on these two entities, which I don't know, what is the optimal encoder of the patterns and what is the optimal decoder of the pattern. Now, using the language of information theory, we can really answer this question in a very interesting and general way. So given this joint distribution of X and Y, so again, in a technical sense, I'm thinking mostly about typical patterns. And of course, in order to do this, I need some concentration results on the nature of the distribution of X, but let's keep this aside for a while. And then I want to find this encoder and decoder. And it turns out that, okay, I don't have to explain it to this audience, I suppose, that the typical representation size in bits, just as in information theory, is completely characterized asymptotically by the mutual information between the representation and the patterns. And this should be more or less obvious to those who know something about, let's say, source coding, or let's say rate-distortion theory in information theory, but exactly the same machinery that works there asymptotically when the block is very large works there, and I'll show you how. Although, again, I'm not talking about communication, I'm talking about how many bits I need to know about X in order to represent it by X hat efficiently. And efficiently is measured by the decoder error. And the natural way to think about the decoder error is to measure how well I can predict the label Y from the representation compared to a prediction from the pattern itself, based on everything that I know about this problem. So essentially, you measure the mismatch, or the code length mismatch, if you want, or loss in this scale divergence between the actual best prediction and the prediction from the representation. So a good representation should have a small KL like this, but it's rather easy to show that this average KL, average over all X and X hats, is precisely the mutual information between X and Y, the original mutual information in the problem. If this mutual information is 0, of course, there's nothing to do. I cannot predict Y from X. So this mutual information should be high in order for the problem to be interesting, high compared to the entropy of Y, minus the mutual information between Y and X hat, which is precisely what you want to do. So minimizing this distortion, this average loss of information due to the representation is precisely equal to the loss of information about Y in the representation. And once this is given, there is a very natural variational question in order to answer the question, my original question, the minimum number of bits that I need to know about X in order to make a good enough prediction on Y. Of course, good enough could be perfect, but that's rarely possible. But I want it to get as high as I can, and I monitor this good enough about Y by this Lagrange multiplier, which we denote by beta, and should remind physicists of the beta of statistical mechanics. But so this is a positive Lagrange multiplier, which should guarantee that this mutual information that the representation has about Y is not too small. So this is the problem we call the information bottleneck variational problem, or the information bottleneck problem. Find the best encoder, or find the encoders which are going to be functions of beta that gives you the minimal information, the minimal number of bits that I need to remember about X, which gives me some reasonable prediction of the unknown property Y. Of course, there is an implicit or explicit Markov chain here. So I assume that I generate my representation as a function of X hat, and my desired label Y is to the left of X. So I know, so this is given by nature. I mean, the connection between X and Y, this is not something which I assume I can control. I mean, of course I can in some cases, but so this is unlike some of the machine learning problems where you put this X set between Y and X. Here I actually look for an encoder of X, which has a lot of information about Y. But then more generally, I'm then using this encoder that I find by solving this variational problem in order to make predictions. So in the prediction problem of learning, I don't have Y, X, X hat. I actually have X, X hat, Y hat. And this is what I call the prediction part of the problem. So for now, forget about this Y hat, which is a predicted label for something I haven't seen. Now the question is, so I just want to very briefly mention to you that because we are talking about biology here, essentially, if you think about biological computation, this is a map, or actually any computation in a physical device. I mean, there is always this abstract computational model, like a Turing machine or automaton or whatever it is, and which is encoded in a physical system or a biological system, which is a physical system, essentially by mapping the input of my computation to some initial state of the system, and then let the physics and dynamics move my system. And then, of course, if this biological computation is good and valid, I should have a decoder which maps the final state of the physical system, which evolves with control or without control. Usually, there's of course a lot of control on the evolution of this system, which is what we call a computer today. But in a physical or a biological system, this is not obvious what is this control and how exactly it is done. But what I really need is to encode my data in the initial state of the physical system and then decode it at the final state. And if this computational model is well implemented by the biology, I have this diagram being commutative. Essentially, I can predict the biology by moving in the other direction in the inverse decoder, or I can encode the state of the system in a computer by using the inverse encoder. So I think that should all, and what is really important for me in this diagram is not only that it has to be commutative, at least on some subsets of interesting questions, but it's the encoder and decoder which really do the interesting part of the story. So remember this, I just want to remind, I'm sure the very few of you who don't remember what these functions are. So the KL divergence, which I already mentioned, is just the average log likelihood ratio of two distribution, which is a non-negative quantity, and it's precisely zero when they are equal. It's a non-symmetric quantity, but it's extremely important measure of information, of course. And the mutual information is just the KL divergence between the joint and the product of the marginal of two variables, which is also the entropy of one variable minus the conditional entropy of this variable on the other one, or if you want how much uncertainty I removed from X when I know Y. And what is really interesting about mutual information is what we call data processing inequality, that along a Markov chain, the mutual information can only go down. I cannot gain information by processing whatever I do, which is, of course, bad news computationally, because it means that any invertible map of my variable, which can be computationally very difficult, like encryption, doesn't change information. So information by itself has to be relaxed to some computational model for which this makes sense. Otherwise, I can embed in mutual information a lot of computational hardness. Now, and just I know that most of you got this, but I'm not going to expand this that too much. So we actually have been playing with this question for some time, at least since the early 90s, and I always thought about it as some sort of extending this classical statistical notion of minimal sufficient statistic. So I want, in the context of parametric statistic, y should be thought as an unknown parameter. And what you're seeing a sample, then you want some function of the sample, which you call statistic. Or actually, you want a minimal sufficient statistic, which is the simplest sample of the function, which still preserves the information about the parameter. And that's an information theoretic way about thinking about minimal sufficient statistics. Unfortunately, minimal sufficient statistics exists for very specific and very special distributions like the exponential forms. So in general, we relax it to not asking all the information about y, but some of it using this Lagrange multiplier method. This is also related, of course, to some generalized Rate-Distortion problem, and it's also an interesting intersection of different type of information measures, and those that are characterized by DPIs, which are the Bregman divergences, and I'm sorry, by something which we call the centroid property, or the average as minimizer, and the F divergences, Fizeau's F divergences, which are characterized by DPI. And it's only this Shannon KL which allows us to play with both of these quantities, which we actually need in our algorithms. So just to summarize, or we end up with a variational problem which is characterized by some sort of a Lagrangian, which is essentially a function of three different maps: the encoder, the decoder, and the marginal on the representation. And we can solve this problem by essentially iterating between these three equations, and the solution is given by extremely simple looking equations. I mean, so the optimal encoder at the given beta is exponential in this scale. It's like a Gibbs distribution with beta multiplied. So this looks like a Gibbs or Boltzmann distribution with this marginal here and z as a normalization. And the optimal decoder is just the base optimal decoder, which is just the average over the data of the encoder. So this is really nice in the sense that these are very simple and very intuitive equations. You can think about them as some sort of clustering or partitioning of the data X into extremely very few discrete representations. I'm not going to get into issues like continuous or discrete variables here. Of course, when X or Y or both are continuous, there are some issues of measurability. Eventually, I'm talking about cases which can be quantized efficiently, and there's a finite. Think about it as discrete or even finite representation, just to simplify the story. But of course, we do think about Gaussian processes and many other continuous variables. So what is really nice about it, that those equations can be solved just by iterating those three self-consistent conditions. And this should remind the information theorists here of the Harimoto-Blaut or the Blaut-Harimoto algorithm for solving the Rate-Distortion problem. It's somewhat different because the distortion here is a function of the encoder, of the decoder itself, and therefore the encoder. So it's a nonlinear type of a non-convex optimization problem in general. But just like in Rate-Distortion problem, we have this very nice two-dimensional picture, I mean, which is what we call the information plan. How much information about the pattern is maintained by the representation? This is what I call the compressed representation information, or the relevant information that I actually need to maintain about X, versus how much this relevant representation gives me about Y. So in general, in the sense that if none of these distributions are precisely zero, none of the original Py given X is precisely 0 or 1, which means the problem is can be even slightly stochastic, then we know that we have a continuous smooth line, which is upward concave, which is a boundary between the achievable representations that a representation can actually achieve with this type of encoder. And above this line, just like in Rate-Distortion theory, there are no solutions to this Rate-Distortion problem. And under this line, there's a zoo, which we are going to explore a little bit, of optimal and suboptimal representations. And there's another interesting line here, which I didn't draw here, but you'll see it later, which is what is the minimum here? I mean, is all this we know that this region is convex. That's very easy to see, just like in Rate-Distortion theory, but there may be a convex limit here below which you cannot go. So that no representation with zero information about Y and some information about X. And this became a very popular problem in the last few years. It's actually the converse in some sense of the information bottleneck problem, and it's called the privacy funnel, which you can see immediately why this is interesting, because it gives you how much information you must reveal about Y if you want to give me some information about X. So this is why it's exactly a security issue or a privacy issue. Both of these problems have this variational formulation. Unfortunately, the privacy funnel problem is not that simple to solve. I mean, there are all sorts of issues there which I don't want to get into. Now, there are many other details in this picture. One of them is this red line. And this red line is essentially what happened if I don't have the distribution of Px, xy, of x and y. I have only a sample, which is, of course, the case in machine learning. And then, of course, there's something strange happened. I mean, you can't really learn very detailed representation, which means where the mutual information of the representation goes very high, there's a gap which is growing exponentially actually in I, for which you are going to lose information if you don't have all the data. This turned out to be very important in machine learning. So the optimal representation of X must lose some information. And this has to do, of course, with overfitting and good generalization. But it's important for my story that if you don't lose some information about X, you're not going to generalize well. The actual information you're going to obtain about Y is going to be a lot lower than you think if you don't have enough data. So this is essentially regularization or dimension reduction of the representation. It cannot be too detailed if you don't have enough data. It's not a big secret to anyone. It's just nice to see how this appears in this information plan. And there are all these blue lines here, which are essentially suboptimal solutions, which always exist, and which are going to be related to these critical points I mentioned to you. So if I don't allow a topology change of my internal representation, the solution is going to take me away from the optimal line at some point and become suboptimal. And then there is this tricky critical point beyond which you cannot go. So think about it as something like splitting the domains or splitting clusters. You have to increase the complexity of the representation in a discrete, interesting way. And this is the meaning of these suboptimal lines. I'll come back to them later on. Okay, so I just want to, this is a very mathematical audience. I want just to give you the gist of the connection between this story and learning theory. And so we already had at least one talk or two talks about the generalization in learning. And you know that machine learning is originally characterized by this wonderful bounds that are due to Valiant and others, which are called PAC bounds, which are essentially telling us that the generalization error, which is the error outside of my sample, is bounded by some nice property, the log cardinality of my representation, which I denote here by the hypothesis class at some measure epsilon, divided by the number of examples that I see. So this with some confidence level, which is actually not so important when we talk about large problems. And usually what happens is when this cardinality has a metric structure, so I can cover it with spheres of size epsilon with a number that grows with some power, some dimension d. So this is the classical Hausdorff dimension or fractal dimension or whatever you want to call it. If I can cover my space, then you see that the log of the cardinality goes like d over m. And this is really the classical results, essentially the number of examples that I need of the order of the dimensionality of this hypothesis class covering. Now, how is this related to information theory? So essentially, again, for those of you, and I'm sure there are many here who know something about the coding theorems of Shannon, what we do by this encoding the pattern X in some internal representation is essentially we learn functions which are constant over these subdomains, and essentially the cardinality of my class goes from the worst case, which is just 2 to the power of X, to 2 to the power of the cardinality, which I denote here by T epsilon. I'll come back to this later on. And this cardinality is dominated by this prediction ability. I just replaced T by X hat by T. It's the same thing, which is bounding some other measures like the L1 norm or L2 norm if you're interested in some sense. So essentially, there's something interesting. Essentially, if I compress my representation, I map X to X hat, I actually map the points, all the possible points of X to points in these clusters or these spheres here. And essentially, in order to prove things, I need to assume typicality in some sense here. And I just want to remind you the issue of typicality in information theory, and which is essentially due to this famous Shannon, Macmillan, Bryman, and so on theorem, that under some very general conditions on the sequence, like ergodicity and stationarity, we can put all sorts of technical details here. The log probability, the average log probability of sequence has a very well-defined limit, which is precisely the entropy or the entropy of the source. And this is true not only when they're IID, but when they have all sorts of factorizable. If I can somehow approximately factorize asymptotically this distribution, I'm going to have this limit, and then the typical patterns are close to this limit, and the probability of typical patterns precisely exponential in the entropy and uniform. So this is very nice, and if this is true for my representation partitions, and of course this has to be justified, then I have this remarkable property that both the mutual information X about X and the mutual information about Y of my representation asymptotically factorized. And so I have this log of a product, and this of course is an assumption about the nature of my patterns, so that I can write, let's say, the probability of a pixel in an image. It's almost completely determined by the probability of some neighborhood of the image, which I call here the parents of the pixel. And if this is true everywhere in my pattern, then I have a central limit theorem. I mean, the log product turns into a sum of conditionally independent terms, and I have this very nice convergence, or concentration, if you want, of the mutual information of the representation. And similar arguments, a little more complicated, but similar line of arguments hold for the mutual information of the decoder. So that's very nice. So I really expect that both of these things under some factorizability conditions, which are precisely true for many of the problems we actually solve with deep learning, like object recognition or image recognition or speech recognition, or I can at least in some approximate sense assume this factorizability, like hidden Markov model for speech or hidden Markov field or whatever, Markov random fields and so on in many other fields. So that's actually very nice, because it gives me this essentially the ability to count the cardinality of my representation by repeating Shannon's argument in coding theorem. So essentially, what is the cardinality of my internal representation is 2 to the age x, which is the typical case. So the entropy is the log of the cardinality. 2 to the entropy is the cardinality, and the cardinality, the typical size of the internal representation, is 2 to the conditional entropy, and this gives me that the cardinality of my representation is precisely 2 to the mutual information, age minus age conditional x. So that's very nice, and actually somewhat surprising, actually very surprising. Don't have to take it seriously. It gives me that any compression of my representation acts like the cardinality of my space in the cardinality. Of course, I'm cheating here, because I'm using the data itself to generate the bound. So this is something which has to be carefully justified. But intuitively, you see this type of bound, that the error in my generalization is related exponentially to the information of my representation compression divided by number of bits, number of samples. So that's this very crude use of the pack bound and this information theoretic approaches. Of course, I introduced the data dependent and problem dependent dependence into this, which and which forced me to be a lot more careful here. But at least this gives us this notion that any bit of compression of my representation is essentially equivalent to doubling the data. So I really want to compress my representation. Now, and we can prove it using a lot more careful arguments. But something like this is true about the complexity, the sample complexity of the decoder of my problem, not the encoder. So okay, so this is again this bound again, which explains this red line that I mentioned before. So the fact that I get this drop between the actual information that I can achieve if I have all the data versus the information that I achieve if I have only a sample of size m is precisely this difference between what I call the empirical information of my sample and the actual information. And this, just reversing the argument in the bound I saw before, is related to the square root of 2 to the I over m. So it's 2 to the I over m again, which gives me this crucial need to shorten the representation, or at least the part of the representation. Of course, I can keep a lot of unnecessary details in my representation, as happens in neural networks, but I'm going to use from decoder only this amount of details about the representation. And in general, we need to worry about these two things. I mean, how much I lose by compressing my representation and how much the finite sample is giving me. And you really want to minimize both of them. And that's why you want your representation to be around the maxima of this red curve. Okay, so this is the gist of the theory. Essentially, the generalization bound is directly related to how much you lose about the y in your representation, and the effective dimensionality of the decoder sample complexity is 2 to the I of the encoder information, and you get this PAC line, but you have to be very careful with it because, as I said, because this is a problem-dependent bound. It's not over the whole class. It depends on the class, on the problem, and of course you need to use it carefully. Okay, so this is the essence of the theory. It tells us that you really want to find efficient encoders which lose a lot of information practically or effectively for the decoder, and then the decoder is just averaging this encoder, and it gives us these information theoretic bounds, which, if everything works well, so if my learning problem actually solved somehow minimizing the complexity, I expect the internal representation of my machine to lie on this line, or on this line actually, in some area which is going to be useful, so where it maximizes the information about the label. So this is somewhat unusual view of the learning theory, because I'm moving from worst case problem independent bounds, but to something which is typical, not worst case, and is problem dependent, but in some sense algorithm independent or architecture independent. But let's see if we can actually apply to the hottest problem in machine learning today, which is deep learning. So deep learning is this late phase of AI, which is now dominating everything, and this structure that I'm sure many of you know. I mean, so we have many layers of neuron or linear threshold gates with all sorts of nonlinearities. And so I take essentially a picture of let's say a dog, and train it over many dogs, and to give me dog or not dog or whatever, by essentially doing what we call error backpropagation, which is nothing more than the chain of derivatives propagated through the layers. And the question we are trying to answer is what happens in the language, this information bottleneck lens, if you want, and what happens to the internal representation along the layers of this problem. So I'm not sure how much time I have, but I'm going to continue until somebody stops me. So essentially, this is what we call the opening.
You have about 10 minutes.
10 minutes. Okay, so I'll show it very quickly because many of you may have seen it somewhere. So essentially, we look at this neural network as in this language of information. How much information about the patterns actually flows through the layers, And we ask, so this is a Markov chain once the weights are given. And so there's a very natural question. I mean, what is the mutual information between the X and each one of the hidden layers? And what is the mutual information between Y and each one of the hidden layer? And let's look at them in some real neural networks. And of course, since we have a DPI, we know that if this is actually the information, of course, there's a big issue, and which was criticized by many people. How do you estimate the mutual information in big problems? But there are many variational and approximate approaches to this, which I'm not going to discuss here. So in some sense, this is a non-issue today for me. But of course, we need to do some sort of quantization and some sort of approximation of these quantities. But in principle, we know that information theoretically, there's a chain, a data processing chain of inequalities. Information in the layers goes down, and information about the label, no, information about X goes down, information about Y also goes down. And essentially, we focus again on the encoder-decoder problem. So how much information of the encoder, how is the information of the encoder and the decoder behaves along the layers of a neural network? Now, I mean, I'm sure that all of you who like biology can immediately see why I can replace this deep learning artificial structure with substrates or tissues in my brain, and in principle ask exactly the same type of question. I mean, if my brain is evolving using some sort of a random-like search, whether it's mutations, whether it's evolution itself, or whether it's some sort of learning processes that happens in my brain by changing synapses, eventually I'm going to converge to the best possible solution that this particular random process can take me. And my claim is that if this is what happens, such a stochastic learning process should take us close to this optimal line, optimal bound, which is the information curve or the information bottleneck bound. And this is a very strong statement, because if this is true, then we have a very concrete prediction about the mutual information encoded at a given layer of the pattern and the mutual information of the prediction. And also we have the exact structure up to some permutation and transformation of the variables, of course, which I don't know, but we have this form of connection between the encoder and the decoder, which the information bottleneck variation problems gives us. So we actually started together with Ravit Ziv to do simulations of neural networks, and I'm sure many of you have seen this movie. But essentially what we do is just plot this information about X versus information about Y for 100 different repetitions, random initializations of the same neural network with 5 or 6 hidden layers we did it in. And essentially the type of pictures that you see, if the information actually goes down, so you actually force the layers to get narrower and narrower here, is this type of dynamics, which is always striking when you see it. So first of all, you see the concentration. I mean, you see that all those layers, despite the fact that they actually belong to very different neural networks, move together. I'm sorry, there's some issue with computation here, but eventually they all move together. Let me show it again. I mean, and they move in a very interesting way. I mean, they first all climb up. Notice that 100, it's a very small problem. There are only 12 bits of inputs, and you already have these concentration results and typicality arguments that I mentioned. We already see it in this simulation. And eventually, at the end of the learning, the last hidden layer, which is these orange circles here, converge to almost perfect minimal sufficient statistic, in the sense that it remembers essentially only 1 bit about the pattern out of possible 12, and predicts exactly 1 bit about it, which means that these are essentially perfect. Now, I want to emphasize that this is the typical picture that we see in many, many different problems. It's not just this problem. You see DPI nicely here, and you see that the more you train it, the more it is pushing to this limit. Now here, the information curve is actually very steep. It's essentially, so the kind of picture that we see is that all the layers are doing this type of evolution from first from A to C, which happens rather quickly, and then from C to E, which happens slowly. So this is some sort of a diffusive motion, and of course many people are thinking about this, including some of you. What is the nature of this diffusion? So there's a drift phase, and then a very noisy gradients which characterize stochastic gradient descent. But we actually see it also with very little noise in the gradients, and we see essentially the same type of diffusive behavior towards a good generalization. So we actually see not only that the layers converge layer by layer to some sort of an optimal bound, but that we can understand, okay, we relate the stochastic nature of the gradients either explicitly or implicitly to these two phases of first drift and then compression of the representation. And then eventually the last layer converges to a very good approximate minimal sufficient statistic. But all the layers seem to follow a similar line of compression. So you can ask all sorts of questions about it. For example, what happens if I don't have data? So generally what we see is that this picture that is trained over enough data, so the representation converges to very nice points on this line. If you don't have enough data, you get this overfitting phenomena. But notice, by the way, that the first phase, the drift phase, is essentially identical, even if you have very little data. So this is not that sensitive to the sample noise. It's a much coarser property of the data to converge to this line. Essentially, you can do it even for random labels. But then the hard part is not losing relevant information when you move when you start to diffuse or start to do this diffusion. So there's a lot of things to understand in these pictures, and of course this has been something we have been struggling with to really get all the details in the right place. But one thing I want to focus on now, so we know that those layers converge to some intermediate points along these lines. They don't converge all the way. And actually, when we look at where they converge to, we can actually show that for small problems, these layers converge to the optimal information theoretic bound. So that's very striking. So first of all, okay, so this stochastic dynamic of the training really takes you to close enough to the optimal bound. But on the optimal bound, we know what the nature of the encoder and the decoder are. I mean, so they satisfy this information bottleneck equation. So this layer, which is actually very close to the beta equal 66 solution of the bottleneck equation, and so on. So this is actually a very strong prediction. I mean, we can actually tell you what is encoded by this layer by comparing it to the information bottleneck solution. And that's precisely what we do. And it's not very easy to see that the layers indeed obey the bottleneck solution and actually encode what we want to encode. But for very small problems, this actually happens. It's very easy to see it. And the interesting question is what and there seem to be very consistent dynamics of these limits. I mean, so we know that it's the gradients that do it. I just want to flash at you one slide here. So we know that in a neural network with SGD, at least with stochastic gradient descent, the gradients are very clean up to some point. The SNR of the gradients is very high, which means that this is essentially a drift dynamics and are very noisy beyond some point. And this is something we see in many, many different problems, which is essentially a signature of convergence to a flat, low-dimensional manifold. So,
can you start to wrap up?
Yeah, I'll start to wrap up. Okay, so this diffusion really explains a lot of the details that we see in this information plan. I just want to mention one point, which is the fact that the more layers you have in your problem, the faster you converge in terms of the number of updates, which again can be explained from this information theoretic perspective. So there are many, many other details here. And the most interesting one is really what characterizes the location of these layers. And again, without getting into many details, I believe this is a conjecture which is just supported by fun simulations, that this location of the layers is related to the critical points of the information bottleneck equations. And I don't have time to actually show you the details. So I'll just summarize by repeating the main point. So essentially, the information bottleneck is an information lens in the sense that it captures the relevant part of a random variable with respect to another one, or essentially it gives me some sort of a magnifying glass on what's relevant and not relevant in this data. And in some sense, it brings back the notion of meaning and relevance into information theory that for some strange reasons historically was ignored. I mean, Shannon himself is partly responsible for that when he said that information has no semantics. Actually, if you just squeeze the relevant bits by this variational problem, you discover again the important sense of which bits are really important for a certain specific goal. And so this is the essence of the information bottleneck, and it gives it in a very constructive or precise analytic structure that allows us to discover many properties of these encoder and decoder pairs. And it's the information plan that tells us a lot of the intrinsic structure, including the topological transitions and which layer represent which. So the layers of neural network really sit on this line, and if I'm efficient, each layer is representing a certain different combination of features, and that's happening gradually and hierarchically along these layers. And of course, there are many other problems which I could mention, like the relation to symmetry and exactly what happens with finite sample bound and variational approximations in relation to randomization and so on. But I'll stop here. So thank you very much.
Thank you, Tali. Great talk. I think that we will have opportunity to talk about and ask questions about this talk later.